Hello, this is Mr. C in France, having a flashback to pandemic year of teaching, making these Edpuzzle videos for my classes. So I'm not going to say it's nice to relive those memories, but it's interesting. So if you look on the screen here, you'll see two displays of the same data. Take a chance to respond to the question that's going to pop up on your screen. All right, most of you probably got it right. What is wrong with the graph on the left is the y-axis is making it be a misleading graph. This is one of many examples of the things that you are going to have to try to avoid when doing your experimental design and analysis speech. So don't do something that makes one set of data look skewed when it's not really quite as intensely different as that one is. Group A looks like it's 3 times as big as groups B and C when provided in a misleading graph like the one on the left. The one on the right obviously shows it more in context and more as a fair comparison of the data. Now, the thing that we have to keep in mind as we go through this is most of the time, this is not done maliciously and it's not done on purpose. Sometimes it is. You want to make sure that you're avoiding obviously doing it on purpose, but also doing it accidentally. So let's get into it. The purpose of this video is to get you thinking about your data and how you can use it. This is really important for your EDA speech because you're collecting data. You want to make sure that you are analyzing it correctly and that you are sharing it with people in ways that make actual statistical, mathematical, scientific sense to the viewer of your video. All right, so in general, just be careful with the conclusions you make from data. I get a lot of these speeches in which people do a version of this. In the United States, 95% of the milk consumed by humans comes from cows and yaks. Obviously not this one specifically, but this kind of a statement, which is totally true, but is it honestly communicated? When 94.999% of it is by cows and only 0.0001 is yaks, it is true to say 95% of the milk is from humans and yaks, but it is a misleading statement and it's not 100% honest. Again, maybe not done intentionally. We want to try to avoid this sort of thing. So the plan for this little video is to talk about the 5 big statistics pitfalls to avoid. First, messing up correlation versus causation. Second is not thinking about mean versus median. Third is not considering if something is statistically significant. Fourth is failing to put numbers in context. And the fifth is just simply using the wrong display for data. So let's talk about that first one, messing up correlation versus causation. This is probably the most famous statistical error. I'm sure that you've heard about this. And so if, let's say I had a group who I didn't give oversight to, and they went ahead and collected data on whether or not drinking Mountain Dew makes them do better in school. All right, and they have this number of bottles of Mountain Dew they drink on the left-hand side and the school rating of how their school day went on the right-hand side, and they want to see if there is a relationship between these two variables. If you have two sets of numbers that go together, you can make a scatter plot. That scatter plot that you make might have a positive correlation, it might have a negative correlation, it might have no correlation at all. The thing to watch for is if you get a positive or a negative correlation, not jumping to the statement that the x-axis causes the y-axis. So you do not want to say, if you get a positive correlation, that drinking Mountain Dew makes you do better at school. You don't want to say that drinking Mountain Dew makes you do worse at school if you get a negative correlation. You want to say that there is a relationship between these two variables that appears in your data, but you cannot jump based on the data that you have to causation. All right, so just be careful with this. Here's a good XKCD comic that tries to get across this idea. I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. Very good insight into this whole issue here. So correlation does not imply causation is the theme. All right, this is a statement. True, 100% of people who drink water die. That's a fact, but don't confuse correlation with causation. This is data that I pulled off the CIA World Factbook website. I made a quick scatter plot of it to see if there is a relationship. The number of TVs per 1,000 people in the countries of the world. Each of these little dots is a country in the on planet Earth, and the y-axis is the life expectancy in that country. There is a pretty good positive correlation between these two variables. And so somebody in a speech or in a paper expressing this might say something like this: the life expectancy increases, the number of TVs per person increases, therefore watching TV causes you to live longer. So what's the flaw in that reasoning? Yes, correlation does not imply causation. The flaw is there is what's called a lurking variable behind this. There is a third thing that is causing both of these to happen in the same direction, and that's just simply GDP, or country income, which leads to the ability to buy more TVs. It also leads to better healthcare outcomes, which leads to better life expectancy. Here's a famous one. This is probably the most famous one that's out there. It's ice cream sales and shark attacks. They are strongly correlated. And the thing that somebody might say to you is, oh my gosh, ice cream causes sharks to attack. All right, well, you wouldn't say that, but it does happen. And this is another perfect example of that lurking variable. The lurking variable is just the weather and the time of year. All right, so things that might be happening. You might actually be having a causal relationship where P causes Q. The x-axis is causing the y-axis to happen. You might have mistakenly put them and have the independent variable on the y, and it might actually be a reverse causal relationship where Q causes P. You might have a lurking variable where M, something else, is causing both P and Q to happen. That sounds very spooky, a lurking variable. Or you might just have a weird coincidence. All right. These things happen all the time, weird coincidences. And so think about your data. Hold open the possibility that it could be any of these. You do not have enough time to get data in this experiment to say causal. You want to say that it potentially causes something. Here's another one. Films Nicolas Cage appeared in and swimming pool drownings are strongly correlated with each other. That is probably just a weird coincidence. Although, having a chance to look at a nice Nick Cage meme is always a good idea. All right, here's another one that comes up all the time with this is sports things, man. People are so superstitious with sports, and it's usually confusing causation with correlation. And so it's like that. I had a really good game today, the best game I've had in years. These must be my lucky socks, right? All right, let's move on to the next one. Mean versus median. If you did a data analysis on whether your strength training course caused people to jump longer for a long jump, you get this data right here. You can see you got 5 people whose lengths increased, and you got Sam who had a tragic event right there. And so the flaw in the reasoning over here, spot it. All right, if you just take those numbers and average them, and you take June plus Carol plus Tom plus Bob plus Augustus plus Sam divided by 6, you get that the strength training program lowered the people's jump average on average. And so that is a flaw in the reasoning, because the mean is what's called sensitive to outliers. The median is what's called resistant to outliers. That SAM data that is an outlier compared to the rest of the dots is very, very weird compared to the rest of the data, and that highly affects the mean and drags the mean down towards it, making the mean way smaller in this example than it should be. The median would be a much better use for this. So if you get data that has an outlier, it's good to show both the mean and the median, but probably focus on the median. Hey, here's another example. Temperatures over the course of a week. If you had this kind of a week, would you say it was a warm week or a cold week? Well, I think 37 degrees, the median, is probably a better measure of what happened this week than the mean, which was 43.86. And it's because of that 98 degrees that is dragging the mean up in this case and skewing it to make it too high. All right. If you ever watch the news, this is always in the news where they talk about the median home price. And the reason why they always sell you on the median home price instead of the mean home price is because of outliers. There are those few multi-million dollar houses compared to the bulk of the houses that are being sold that drag up the mean artificially. And so it's always in these articles that you get median instead of mean because of the outlier. So here is an actual like graph of what the house prices would be in a town. As you can see, you've got all of those small bars up to the right that are the outliers. They will drag that average or mean up higher than the median. In this case, the median would be a much more accurate representation of the true center of this data rather than the mean. All right, here's another example. This is an example of it happening intentionally, where somebody's actually trying to mess with you. If you had a company that was putting out an ad that said, apply for our company, we're a wonderful place to work, the pay is great, the average salary of our employees is over $98,000. If you took 25,000 10 times, 40,000 20 times, and then a boss that makes $2 million, that is accurate. But is it truthful? And it's not, because the mean is $98,387, but the median is $40,000 if you put all these numbers in order, which is a truer number for the actual what you might make working for this company. It's obviously the median. All right, this happens with tests. Let's say that you took 7 tests and your unit 6 was really bad. Looking at this kid, Jimmy, I think most people would make the case that Jimmy probably deserves a B. He gets a B on almost everything. But if you look at Jimmy's mean, he has a 76%. If you look at Jimmy's median, he has an 83%. I'm hoping this can help you actually use this in your real life. Hint, hint, nudge, nudge, wink, wink. All right, third thing, we're going through this. Not considering is something statistically significant. And so if you look at this, say a group did this data and they watered a plant with 6 different types of water, and then they measured the height of it. You said, after watering the plants for 2 weeks, we saw that the tallest plant was watered with smart water and the shortest plant was watered with seltzer water. Therefore, smart water is the best thing to water your plants with and seltzer is the worst. Well, look at smart water. It was 23.7. Look at seltzer water, it's 21.9. We don't know if that is just something that could have happened through natural differences. If you had bought just 6 plants and watered them with tap water, you might have already had that amount of variation. You would actually need to have that data in order to make this case. The chi-squared group could probably help you out with this a little bit, but you cannot say that it definitely made a difference and that smart water was high enough to be the true best. Okay, so you do not know if it's statistically significant. You can say that it looks like from our data, the smart water might have led to the best plant growth. All right, so for differences in data, you just don't have all of this. You have not taken AP stats yet. If you're interested in this, and this is actually kind of something that makes you go, really think about taking AP stats. It's one of the most interesting classes you can take. It could just be normal variations in these differences, though. All right, you don't have the knowledge of confidence intervals, p-values, normal distributions, chi-squared, and other statistical ideas to make firm predictions or conclusions. So don't overemphasize differences in results unless they are absolutely clear. Ask yourself with your data, is it statistically significant? All right, failing to put numbers in context. Here is an actual copy of a paragraph from a log from a couple of years ago. This person wrote all of this. You can pause the video and read it if you want to, but my comments on it right here was this. The person said in the US, they calculate that 1,339 trillion watts could be generated over a year or unharvested. Well, I'm like, that's quantification, but it still lacks context. 1.3 trillion watts is neither a small or a big number in and of itself. What percentage of the total power consumption of the US does it represent? There's no such thing as a big number or a small number. All numbers are in context with each other and how they compare. Maybe 1.3 trillion watts is a lot. Maybe it's a small fraction of the overall usage. I don't know. You have to put your numbers in context. The student went and researched this and found that this was this percentage of the total number of watt hours used in the United States. So it wasn't nearly as impressive as they thought it was when they were just like, ooh, big number, right? All right, so put the numbers in context. 5 million out of what? When you say most, you literally mean more than half. Can you back that up? Don't use the word most unless you mean literally more than half. Again, nothing is big or small in and of itself. Everything is relative. All right, last thing. Thanks for sticking with me here. Using the wrong display is a huge flaw as well. So think about qualitative versus quantitative. Some of you have only quantitative data. Some of you have a mixture of qualitative and quantitative. Make sure that you are careful with those and make sure you're super careful with your line graphs, okay? You would use a histogram for quantitative. Notice how there's no gaps. The bars touch each other. The x-axis are numbers. The qualitative one, you make a bar chart or a bar graph. Notice how there are gaps, that the categories of the x-axis are not number-based, but they are category-based. They are words, not numbers. All right. Again, quantitative, you could actually make a box and whisker plot if you wanted to, where you can see where the 25 percentile marks land, or you could make a pie chart if you had qualitative data. All right. And then line graphs. You want to make sure that you are not making a line graph inappropriately. The one on the left, where you are connecting executives to marketing, to IT, to sales, to finance, to HR, is an inappropriate use of a line graph because those don't necessarily connect to each other. There's nothing that trended from executives to marketing, to IT, to sales. So a bar graph would have been a much better choice for that than a line graph. Okay. The temperature on the 1st of September that goes 9 a.m., 10 a.m., 11 a.m., 12 p.m. That makes sense to have a line graph because something actually happened between 10 a.m. and 11 a.m. that makes sense to connect with a line to imply that the temperature probably rose between those two time frames. All right, so that one's bad. All right, how to categorize qualitative data. If you get something from somebody in your data that looks a lot like this, and you said, what sorts of things make you feel happy with your life? First off, I wouldn't have approved this question, but let's say you get this and your responses are all of these things. How are you going to display this data? Well, this data, you need to think about categorizing. So I took that data and I categorized it into several different categories. I said, all right, all of the sort of like reddish fuchsia things there are families and friends and live things. Nice people, my sister, my mom, when my parents are home, my dog. All of the yellow things were being active and doing things. All of the green things were sleep related. All of the blue things were technology related, right? So we can categorize them and actually get a decent version of the data rather than just scattered all over the place. Okay, so remember, science and data does not ever prove anything. We are not proving. You prove when you are doing mathematical theorems. You do not prove when you are doing science. Only math can do proof. Scientific findings provide evidence that tend to support or deny a conclusion. That's what you're doing here, is you are getting evidence that tends to support or tends to deny a conclusion. It's not a weakness of science, it's actually a strength, because we don't want to just run one study and say we have all of the answers, right? Somebody else could take your data and try to replicate it and see if they get the same sort of thing. Scientists are actually trying to prove each other wrong most of the time rather than prove each other right. So it's always better to make statements that use words and phrases like supports, tends to indicate, gives us reason to believe, than to make grand conclusions that you can't support. So think about that as you're using your data. Be careful out there. All right. I want to see good high-level analysis. Analyze your data like you are high-level STEM students. Don't take shortcuts and don't make basic science errors. Along the way, please realize I'm here for you. All right. Thanks, guys. Appreciate you watching this.